Welcome back to elementary statistics. In this video, I want to talk about Pearson's R, which is a measure we can use to talk about how nicely a set of data, a scatter plot, fits into a linear curve, how closely correlated the data is. More technically, we should call this measurement the Pearson product moment correlation coefficient. I'm not even going to bother writing that whole thing down, but I will mention that you might see it abbreviated as PPMC or PPMCC. We use the letter R to represent this thing, and calling it an R value is far and away more common, but you will see that from time to time, including very often on a lookup table for finding what the appropriate value for a particular situation might be. Looking at this scatter plot qualitatively, we can see that it looks like it is relatively linear. There's definitely a pattern, hard for me to point, but going in this direction, there is a pattern in the data. I should just draw. The point of having this and an interactive whiteboard is that I can draw on it. So we have what appears to be a correlation that is likely linear and is fairly positive in orientation. And so the question we want to ask is, given this data, is the correlation statistically significant? Can we use it to perform hypothesis, or can we use it to perform predictions? And so we will answer that question by way of a hypothesis test. If I get my head out of the way, the null hypothesis is that the data is not correlated. The patterns that you see in the data are entirely due to chance and your wish that the data is correlated. And the alternative hypothesis is that there is a predictive correlation in this data. I'm going to keep the table along with me. I'm going to need that again in a little bit. So let me copy it now while I'm thinking about it and while it's on the screen. For your purposes, you will probably be able to see it again, but I will tell you now that we're going to want to redraw it. The actual scatter plot itself is not something we're going to need to look at. It is an important first step. Look at your data and make sure that it appears to be linear before you start doing a hypothesis test, because you can be surprised at some of the strange things that you might see show up. I'm also going to write down this formula now. It is going to look like a whole bunch of nonsense, but I want to take a little bit of time to try to work our way through understanding what it says. So the first thing that I want you to notice is that this is a bit of an algebraic nightmare. There is a fraction, there is a square root underneath the fraction. And there are a whole bunch of things that involve that Greek letter sigma that means sum. Add all these things together. And so that in and of itself is intimidating. But once we take a deep breath and we realize that if we take our time and we work through this carefully, it absolutely can make sense, we can get a lot more comfortable with this. A lot of the variables that show up in this, all those summations, are just values from the set of data. And so if I bring that set of data back, why is it, come on, there we go. If I bring that set of data back, we can work with it and try to get all of these values. So looking at the formula is scary, but it's really just a matter of all of these things, n, sigma xy, sigma x, sigma y, n, sigma x squared, sigma x, n, sigma y squared, sigma y. Those are all numbers. We're going to figure out what numbers to put in. We're going to put all the numbers in the right place, and then we'll be able to punch it into a calculator, and that will take care of all the hard work for us. And so our approach is very similar to the approach we used for standard deviation. We're going to take our table and start extending it. So I have an X column, I have a Y column. I can create a new column for X squared. I can create a new column for Y squared, and I can create a new column for X times Y. I should mention, I probably should have mentioned before now, that I'm intentionally not giving a story to this data. I'm just looking at a couple of numbers to show you the process. But in your set of data, if you are collecting data out of some sort of a study, your data has meaning. You figure out what your independent variable is, you plug it in as X. You figure out what your dependent variable is, you put it in place of Y here. Your table might be longer than this, but this is going to be incredibly tedious, so we're not really going to spend much time looking at data that involves more than this many data points. I should also come over to the side of the page here. N has been all semester and will continue to be the number of data points in the distribution. In this case, there are 7 of them. And then we calculate line by line. In the first line, x is 5. So x squared is 5 squared, or 25. Y is 6. 6 squared is 36. And x times y, 5 times 6 is 30. In the second line, 5 squared is 25, 8 squared is 64, 5 times 8 is 40. Then we'll have 36, 49, and 42. This particular data set has numbers that we can work with pretty easily. In a situation with uglier numbers, you would just be grabbing your calculator out and doing a bunch of computations, or you'd be going to spreadsheet software and telling it to do the work for you. All right, but we just square a bunch of numbers, we multiply a bunch of numbers together, and we get this completed table. Then remember that that sigma means add it all together. So we want to add together all of the x values. We will get that the sum of all x values is 5 plus 5 plus 6 plus 6 plus 7 plus 7 plus 8. 44. And then we'll just continue column by column. We will add together all of the y values. I get 56. We'll add together all of the x squared values. I don't have quite enough space to put all of this into a neat row, but I would love to have had why is that showing up? I would have loved to have had the notation here of sum x squared actually show up underneath the x column. Unfortunately, that did not work. I have no idea why that keeps showing up, but I get the value there is 284. The sum of all of the y squareds is 456, and the sum of all of the x times y's is 357. Again, just column by column, I'm adding everything together in that column to get a nice single value. I don't need the table anymore. All I need is these entries, and the n that got scrolled off the screen is still 7. Our formula for r hasn't changed. It's just a matter now of plugging in all of the numbers. Again, everything here is a known value. It's just plug it all in. N is 7. Sigma xy is 357. Sigma x is 44. Sigma y is 56. N is still 7. Sigma x squared is 284. Sigma x is 44. N is still 7. Sigma y squared is 456. Sigma y is 56. And from here, we can turn to our calculator. You can do this whole thing in one go if you are confident in your ability to use your calculator. I'm not confident in my ability to use my calculator like that, so I'm going to look at this in a couple of pieces. I'm going to go ahead and calculate everything that's in the numerator as one piece. I'm going to calculate everything that's in this square bracket as one piece. And I'm going to calculate everything that's in this square bracket as one piece. All right, following the order of operations, following those rules from algebra, I know that this process will work. I know that the order of operations says calculate the stuff in the numerator. In the denominator, calculate the stuff in the parentheses, then multiply it together, then take the square root, then divide everything. And so I know that I can split it up like this. Everything will be fine. And it saves me from having to trust my calculator to punch the whole thing in at once. Because quite frankly, I don't. I do not trust myself to type that much in without making a mistake. All right, but 7 times 357 minus 44 times 56, my calculator tells me is 35. 7 times 284 minus 44 squared, my calculator tells me is 52. 7 times 456 minus 56 squared, my calculator tells me, is 56. Now I can do the rest of that work in the denominator. I'm taking the square root of 52 times 56. My calculator tells me that this is an ugly decimal number. That starts off 53.96. And when I perform the division, 35 divided by 53.96, my calculator gives me the number 0.649. That seems like a good place to round it. Most tables are going to have three digits after the decimal point on the value of R, so that seems like a good place to round our result here as well. A couple of ideas about the properties of the value of R. If you really dig into the algebra, you can actually verify that these things are going to happen. I don't think it's worth taking the time to do so, but the value of R is always going to be a decimal number. At its largest, it is going to be +1. At its smallest, it's going to be -1. And generally, it's going to be somewhere in between. Whenever the value of R is positive, there is going to be a positive linear correlation in the data. Whenever the value of R is negative, there is going to be a negative linear correlation in the data. Whenever the value of R is close to 0, that means that there is no correlation. And so the question we have left to answer is, now that I have this value of R, how do I determine if it is actually meaningful? How do I determine if the correlation we see here is actually statistically significant that I can use it to make predictions? And to do that, we're going to use a lookup table, much like the tables we've used for the z-score and for the t-score. We need to set a confidence level. I very frequently use alpha equals 0.05, but it's not the only choice. Then, just like with the t-test, we are going to need to know the degrees of freedom. It turns out that for 2-parameter data and the R-test, you can find the degrees of freedom by taking n minus 2. In this case, n was 7, so n minus 2 is 5. And that's the values that we need to look up on our table. Let's jump over now to a nice table of correlation values. This particular table calls the level of significance P instead of alpha, and it reminds us that the degrees of freedom is n minus 2. That's very convenient. We said we wanted alpha to be 0.05, so we're looking at this column. And at 5 on this column, we have 0.754. So I'm going to come over here and I'm going to write that the critical R equals 0.754. And the rule of the hypothesis test is a very simple comparison. If the R value that you come up with is greater than the critical R value, you reject the null hypothesis and accept the alternative hypothesis. If the R value that you come up with is less than the critical R value, you accept the null hypothesis. In this case, our R value, 0.649, is smaller than the critical R value, 0.754. And so we are going to reject the alternative hypothesis. We're going to accept the null hypothesis. And with what we have, we cannot distinguish our correlation from noise. There is no confidence in the correlation to within 95% accuracy. Right. If we had used a different threshold for our confidence level, we might have gotten a different result. Changing your confidence level is never a good idea. You set your confidence level well before you start anything else. In practice, what we really needed was more data. The regression that we were analyzing looked like it was linear. It looked like there was a nice pattern there. But because there was only 7 data points, actually observing that pattern in a statistically significant way is very difficult. The more data points you have, the more generous the Pearson R test actually is. And so if we have a value, we can approach it, we can make things work, and we can try our best. Sometimes the data behaves, sometimes the data does not behave. Again, the null hypothesis that we accept here is not that there is no correlation. The null hypothesis is that our data does not support a correlation. Let's take a look at one more. I want to go through this pretty quickly because the calculation is tedious enough and we've dwelled on it enough once. But let's take a look at this set of data. Again, I'm not providing a context because we have enough time devoted to the actual performing the calculation, but you collect data, you have an independent variable called x, which had values of 1, 2, 3, 4, and 5. You have a dependent variable, which we call y, which came out as 5, 4, 3, 2, and 1 respectively. You extend your table by introducing columns for x squared, y squared, and xy. You multiply all of these things out. And you add each column together. I get that the sum of the x values is 15, the sum of the y values is 15, the sum of the x squared is 55, the sum of the y squared is 55, the sum of the x y's is 35, and there are 5 values on the table. Again, I'm using some very simple numbers here because actually taking the time to perform all of the arithmetic is tedious, and watching me do that is not a valuable use of your time. Watching me do the algebra from there of plugging things into the formula, I think is a more valuable use of your time. The formula is the same. R is n times sigma xy minus sigma x sigma y all over the square root of n sigma x squared minus sigma x the whole thing squared. times the same thing in y, n times sigma y squared minus sigma y, the whole thing squared. And all of those are numbers we just calculated in our table. So we just plug everything in. N is 5, sigma xy is 35, sigma x is 15, sigma y is 15. N is 5, sigma x squared is 55, sigma x is 15, and we square it. And we have 5, we have 55, we have 15. Right? The symmetry of this particular data set means that there's a lot of things repeating, which is why this is a little bit harder to follow. The numbers are easier, but because there's so many repeated numbers, it's harder to see what is exactly happening here. Which is part of why I'm going through it so quickly. We're just plugging all the numbers in, we're plugging it into our calculator. It might take us a couple of steps. Great. But again, take care of what's in the numerator. Take care of what's in this square bracket, take care of what's in this square bracket. You don't technically have to break it down into that many pieces, but I find that that's a good place to stop and get enough done that it's worth having done, but not so much that you're going to make a mistake. I get negative 50 in the numerator. I get square root of 50 times 50. The square root of 50 times 50 is 50, and negative 50 divided by 50 is negative 1. All right, this is a perfect negative correlation. It doesn't get larger than this, so we know that this is going to be statistically significant. But it feels a little bit weird. All right. I'm going to still use my alpha level of 0.05 because that's the one I happen to like. It's the one I've used in the past. But the specifics of what you're doing, why you're doing it, who you're doing it for perhaps, will determine the level of significance that's appropriate. There were 5 entries in this, so the degrees of freedom is 5 minus 2, which is 3. And if we go to our nice table of Pearson R values, degrees of freedom are 3, alpha is 0.05, the critical value is 0.878. All right, and now we have something weird. Because I said that if R was bigger than the critical value, we reject the null hypothesis. If R is smaller than the critical value, we accept the null hypothesis. And negative 1 is definitely smaller than positive 0.878. I left this out of the first example because we had a positive linear relation and it didn't really make a difference. But when you have a negative linear relation like you have in this case, or a negative correlation of any sort, you have to take the absolute value of the R value in order to do this comparison. And the absolute value of negative 1 is positive 1, which is definitely bigger than 0.878. So we reject the null hypothesis. We reject the claim that there is that the apparent relation is due to chance, and we accept the alternative hypothesis, which is that there is a statistically meaningful predictive power of this correlation. All right. A lot of crunchy math there, not a lot otherwise. But I think with that, I'm going to wrap up. As always, thanks for joining me. I'll see you next time.